Let's talk an example on equilibrium. So we have a beam here, and that beam is connected by a wire such that the wire makes an angle 30 degree with the beam. The length of the beam, though it's not required, but let's say the length of the beam is 2 meters and the mass of the beam is 10 kilograms. Okay, so the question is, how much tension is present in the wire, and the other thing is how much force, how much upward force this hinge here is providing to the beam, right? That is the question. So the first question is F, and how much is T, tension T. Okay, so whenever we solve a problem like this, or in fact any problem in mechanics, we make free body diagram. So we have the beam here, and we have a force F which is being provided by the support, and the force of gravity which is acting here, m times g, and there's a tension that is acting like that, and this angle we know is 30 degrees. Okay, you can define this as the x-axis and this as the y-axis. Or you can define here y-axis, also the y-axis. So for this guy to stay in equilibrium, we know that the sum of forces, we already have talked about that, the sum of forces and the sum of torque should be 0. So what is the sum of forces acting? Equals 0. What does that mean? That means simply, again, as we have already talked, we can break it into two axes, fx and fy. They both should be 0. Sum of forces, sum of all the forces in the x direction and sum of all the forces in y direction should be 0. So let's start with x. Okay. Well, as we are being asked, just the force which is being provided by the by the beam in the y direction, I mean by the hinge in the y direction, we actually are not really too much worried about this equation. We are actually more concerned about that equation, which means that T, again, now T is neither in the x direction nor in the y direction, so we can break T into two parts. T is T sine 30 in this direction, and T is T cos 30 in this direction. Well, you can see, you can either say T cos 30 in this direction, or you can also say T cos 150 T cos 150 in this direction. It's the same thing. That's how we break vectors. If you have a vector like that, which makes an angle theta with the x-axis, we break it as r cos theta and r sin theta, without putting an extra sign here. But we already have defined this to be the direction. We have not really defined direction. Now this is direction in the x-axis, positive x-axis direction, and this is direction in the positive y-axis direction. But here we are defining direction in the negative x direction and writing as t cos 30, which is same as t cos 150 in the positive x direction. So just please be careful when you write vectors like this. This always means in the positive x direction and the positive y direction. But here you can always draw arrow in on the opposite x direction, and you can say this is t cos 30 by simply considering the angle the vector makes with the negative x-axis. Okay, so that gives us t cos 30 degree, t in fact sine 30 degree because we are talking about the y-axis direction, minus mg plus f equals 0. Okay, so this is sum of forces in the y direction. How about torque? So the net torque should also be 0. And what are the two forces? I mean, well, when you say the net torque, the net torque about what? About this point, about that point, about this point, about this point, which point? About which point the net torque? Because torque depends on the radius also. Well, the answer is that you can do an experiment, and whichever point you calculate torque about is going to come out the same. Because torque is in the z direction, and you can always move z direction in at any point. So moving z direction does not really make any difference here, because z is out of the plane. And because physics should not change or depend on the direction of z-axis, or I mean on the position of z-axis, whether it's here or it's here, the torque should always come out to be the same value. So let's choose this as the position of z-axis. So this is the x-axis, this is the y-axis, and coming out of the plane is the z-axis. So let's find out torque. How much is the torque provided by the force F about this point? Well, the answer is 0, because you see the point, the force F itself is passing through the hinge, which means there is no radius present. And for torque to present, we know that torque is given as R times F perpendicular. So this is 0. How about that? This mass. Now this mass is going to rotate rotate the mass clockwise, or rotate the beam clockwise. So if it's rotating the beam clockwise, that means torque is going, if you curl your fingers around the direction of motion, that means the torque is pointing inside the screen, it's going in the screen. So you can write mg multiplied by 1 as the torque provided by this force, but with a negative sign, because it's going down in the plane, and we already have assumed z to be coming out of the plane, plus t sine 30. We know sine 30 is 1/2, so you can just write t over 2 multiplied by 2, because that is the force, that is F perpendicular. So this is R and this is F perpendicular, that is going to move the beam in the anti-clockwise direction or counterclockwise direction. And if you curl the fingers counterclockwise, your thumb points out of the screen. So that gives us t over 2 is the force, and 2 is the distance, this distance. This should also be 0. What does that give? That gives T equals mg. So we know the tension. The tension is same as mg, which is same as 100 Newton if you take g to be 10. Okay, so this is tension. How should we calculate force now? Well, we know T and we know F. So mg, we can calculate F from here. T in sine 30 we already know is 1 over 2 times T minus mg plus F equals 0. Now, T over 2 is 50 minus, what is mg? 100 plus F equals 0. And that gives us F equals 50 Newton. So that is the answer. Okay, in the next lecture we'll talk a little more difficult example.